Right, so how to train your neural network. So we have some neural network with weights and biases and so on. That's our parameters that we can adjust. And we have some input, and that gives us some output for these certain parameters, and then we want to adjust these parameters to get the output closer to what we actually want. Now, to do this, let's think about supervised learning here. So, image classification, for example. You have a number of images, can be these handwritten digits, that's a common test set. And you have a few thousand of them, say, and humans have said that, sat there and labeled them and say this is a 1, this is a 3, this is a 7. So, and you have this set of training data. Now, how do you adjust the weights and biases to get the output from the network that matches the labels when you're training data? And we can keep in mind here that these weights and biases, if there's a large network, we have several hidden layers. It's a deep network, many neurons in each layer, many connections between different neurons and so on. We can easily have thousands, hundreds of thousands, millions of parameters here. And the number of parameters can be much larger than the number of training data we have. So, to be able to sort of get closer to the right desired output, we need to have a measure for how far are we from the right output. And that's done by some cost function, or it's sometimes called loss function or objective function. And it's some function of the weights and the biases. So for example, you can have this quadratic cost function. So here you have number of examples, and you sum for each example x. You see what is the desired output and you compare it to the actual output. So here you sum up the square of the deviations. this is the mean squared error. So we want to minimize this cost function that corresponds to our network working properly. Now, okay, one way to minimize a function would be to find its derivative, set the derivative to 0 and solve that to find the extrema. But we have way too many variables here for that to be feasible. So we need to do something more like gradient descent method. Some search optimization method to minimize this cost function. Okay, I cannot go into the details here, but because it would take too long. So if we are going to do gradient descent, well, then we need to compute the gradient. And there are just so many variables in this function that is not a simple calculation. And it's furthermore, we would need to compute it for sort of all the training examples here. To see sort of for each input x, how would the output change if I change one of these weights and bias? And you would need to do that over and over. That is unfeasible. So there are two tricks here that are sort of essential to making machine learning feasible. Yeah. And one is stochastic gradient descent. Which is basically that you only use some of the training data in each step. So you have this maybe 10,000 data points or so, but you only use 1,000 or 100 of them in each step of calculation to speed things up. And then in the next step you use another 100 or another 1,000 until you use the whole set. And then you start over again. Now, even if you do this, say you can reduce the computational time by an order or two of magnitude. There's still this problem that you need to compute the gradient you need to compute partial derivatives with respect to each and every weight and bias. And as I said, these could be millions of parameters. So how would you compute these partial derivatives? usually, naively.
You see the chain rule? Like start from left to right, or I guess right to left.
Okay, so you already know the trick. So well, okay, the naive approach would be that you would feed the network the certain input for a certain set of parameters, see what comes out. Then you change one of the parameters slightly. You feed the same input and see what the output is, and you see what the difference in output is for that small difference in one of the parameters. And you do the same for the next parameter, and the next, and so on. But this is too cumbersome, it takes too much time. So there is a trick called backpropagation. And basically it cuts down the computational time by many orders of magnitude, because you would instead of having to run this go through the network once for every parameter and to see its change, you just run through the network one time and note down what all the intermediate values for outputs in hidden layers and so on are. And then you go start at the output and sort of propagate back through the network. And you can sequentially there extract all the partial derivatives with respect to each and every one of these weights and biases in just one go. The details of how to do this, I would say, is outside the scope of this course, because we're doing quantum machine learning, not classical machine learning. But it is very important, classical machine learning.
Do you have a good reference to read about it?
There is a book by Michael Nielsen, the same Michael Nielsen as in Nielsen and Tran. Quantum information textbook. Michael Nielsen has written an online short introduction to machine learning. I think you just Google Michael Nielsen machine learning, you will find it. And that's the best explanation I've seen of how this backpropagation works. But as Andreas was saying, it has to do with the chain rule computation. Yes?
I'd also recommend 3 Blue 1 Brown on YouTube. He's really good.
3 blue, 1 brown.
Yeah, he's a mathematician who likes doing pedagogic videos about math stuff like this.
Okay, so with these tricks, you sort of get down the computational time for training to something manageable. And then you can So you can have different cost functions that some, depending on what the problem is you're trying to solve, some cost functions are better suited than this mean square error, for example. Then you can ask questions like, okay, we have these millions of parameters, much more than our training data, as I said. Won't we overfit things? I mean, you might have heard this von Neumann quote, or alleged quote, that if you give him 4 variables, you can fit an elephant, and with 5 you can wiggle its trunk. Now we have millions of parameters. And well, there are various strategies for this. You keep some more, you don't use all the training data, you use some data just to a separate test to make sure that you're not overfitting to exactly the data you're using all the time. But this is also sort of beyond what we have time for here. It's good to know. Right. So, to sort of finish up the classical part here. Why is classical machine learning so successful? Does anyone have something to?
Is it?
Is it? Yes.
Basically, because YouTube and Google and many companies make millions from it.
How many companies make millions from it?
Many.
No. Like 4.
That's plural for companies.
Okay, but why are they making millions from it? Like why is it working? Why does it work now and not 10 or 20 years ago?
We have a lot of data.
Yes, so people usually talk about 3 reasons for the success of ML. One is definitely data. We have access to a lot more data today, and people have put together data sets labeled by humans that can be used to train. It makes a difference if you just have 100 data points to train on, or if you have 10,000 or 100,000. You need to pass some threshold probably before you really see a good result. Okay. Usually 2 more things are mentioned here.
People find success with machine learning in practice. That's the reason for its success.
Okay, but okay, so then why are they finding success in practice? So what's the is there some underlying reason?
Computational power.
Computational power, yes. Computers have gotten much more powerful in the past decades. And again, it seems like you need to pass some threshold for this to really, like, you can really simulate large enough neural networks, say, handle all that data. I mean, we mentioned this and discussed in the break also these Go or StarCraft playing programs from DeepMind. I mean, they say they trained this I think for the chess one, they said they just trained it for 10 hours, and then it was from 0, and then it was better than the best existing chess playing program out there. But when they say 10 hours, that's 10 hours on one or many of Google's server farms with their special built hardware. So yeah, you need power. And then the final thing that's usually mentioned is algorithms. So people have come up with clever algorithms. It's, for example, hard to imagine how neural networks would be trained efficiently without backpropagation. Okay, that is quite old, but that's also many of the more sort of there are many more recent techniques, for example, to avoid this overfitting and so on, that is just from the past few years that were not known in the community before. Okay. So now let's start talking a little bit about quantum stuff again. Or are there any more questions about classical machine learning? Okay, we saw somewhat, at least in the classical part here, that machine learning has a lot of linear algebra. You can manipulate things, think of things as matrices and vectors and so on. So when you think about then doing some machine learning with quantum computers, you might look and see, okay, what are quantum computers good at linear algebra? So do we have some quantum version of BLAS, basic linear algebra subprograms? Well, this is the advanced quantum algorithms course. We are near its end. So you have hopefully heard of some quantum algorithm, either in this course or in some previous course. Although I realize that we haven't perhaps covered much of these particular algorithms in this course. You know some quantum algorithm that can handle some linear algebra problems.
HHL?
HHL, yes. what does HHL do? Roughly.
I don't remember. I knew it's something with,
It's something with linear algebra.
yes.
Okay, so HHL is an algorithm named after its three inventors, Harrow, Hassidim, Lloyd, which solves systems of linear equations.
In some form, right? Not generally.
It's quite general, but then there are some caveats for how it actually works. So. And this is actually exponential speed up. So if you have n equations, this is solved on order of log n steps time. Anything else? Well, I have the quantum Fourier transform. I don't know if you count this as linear algebra or not. We have quantum phase estimation. And with quantum phase estimation, you can find eigenvectors and eigenvalues. That's certainly a linear algebra problem. Actually, all of these have exponential speedups compared to classical counterparts. So that's great. We have our quantum basic linear algebra subprograms. Everything is exponential speedup. Machine learning is solved. It's unfortunately not quite that simple. So there is a paper from 2015 in Nature Physics that's called Read the Fine Print. Or it's not a paper, it's an article or commentary. By Scott Aronson in Nature Physics, I think, which points out the problems and basically there are two problems that people talk about, and those are called the input problem and the output problem. So what's the input problem? Well, if you take HHL, for example, to have this speed up, that algorithm assumes that you can prepare this vector B efficiently in a quantum encoding. So HHL assumes that B can be encoded in in the amplitudes of some superposition. So basically that the jth element in B becomes the amplitude for the jth computational statement. Now, if you can do this, then if B has a length n, then you can encode it using just log n qubits. However, this is called sometimes a quantum RAM or quantum random access memory. And the thing is, if you can do this, if you can take your classical data vector B, encode it like this, and then you can run HHL on this, and you get the exponential speed up. But the process of encoding is not trivial, and turns out basically here what Scott Aronson is saying is that if you can't do it in some smart way, which no one knows yet as far as I know, then this negates all the speed up. The time you need to spend on encoding things correctly on your quantum computer before you actually start your quantum algorithm, that negates all the speed up that you can have from the algorithm itself.
So this is similar to what algorithm for Grover search as well. That
Yeah.
the time you spend, well, if it's unsorted, but if you have to encode it in a quantum computer, you already looked at all the possible solutions.
Yeah. Someone said you can't Grover a phone book. A classical phone book at least. I think it's it's similar. It's a little different since this is not about doing the search in B or so. But yeah, the basic problem is the same. You need to encode it in a quantum form, and that process itself is time consuming. And there is a review on quantum machine learning in Nature from 2017. If I remember correctly from there they talk about machine learning problems that sort of could be using quantum glass. And I think they said that all but one algorithm that they could find there require this quantum random access memory. which no one knows how to do well yet. For hopefully there's a yet there, but otherwise we need to be more clever with what algorithms we actually use on the quantum computer. So this is the input problem. That you need to encode the input in some suitable quantum form, and that's a difficult problem.
I just have a question.
Yes.
Maybe this is a problem as well. So let's say your vector B is very long and its entries are very large, like say one entry is a billion. And then if you encode that entry as a complex number of some eigenstate, because you need to have them normalized as well. I guess to normalize it, you divide with the sum of your vector or something.
Yeah.
Vector B. And then the number would be extremely small, like the BJ that you have in front.
Mm.
And then it's maybe a problem with precision reading out that
It
value.
could
Or maybe
be,
you don't
yes.
need to read it.
Well, you're not reading out B, but yeah, I guess that could be a problem, yes. There can be also different properties of this matrix A here, and not only the size but also what's called the condition number, which also comes into how fast the algorithm actually is. So there are examples. I think you may have heard of Ewing Tang's work where she has found some classical quantum-inspired versions of what was thought to be purely quantum algorithms. And these classical versions, they scale better than expected than with the size of the problem, but they can have horrible scaling with this condition number instead. That again might make them infeasible in practice. Okay, then you have the output problem. And again, we can use this HHL algorithm as an example. So when you run this HHL algorithm, you want the solution to the system of linear equations is this vector x. But what you actually get when you run HHL is not that your computer spits out x. It ends up in some state where you can do some measurements. You can sample sort of properties of this solution vector x, but you don't get x explicitly. So you sort of need to ask for the right things for this algorithm to be used. And that, of course, is a problem then if you're thinking about using these as part of some subroutine to some larger linear algebra problem, that if the output is not the actual solution but just gives you some information about the solution, it can be hard to use that as a following step. So it's hard. The input problem is it's hard to encode the input as in the form needed for the quantum computer to handle. The output problem is that well, even these algorithms with their speed ups, they are not actually giving the exact answer that you're looking for, but they are giving you parts of the solution, or properties of the solution, but not the full solution. Okay, I think that's a good place to stop for today. And then, as I said, the plan is for the next 2 sessions that we first look at some non-neural network quantum machine learning next time, and then some quantum neural networks last time. Okay.